Organic Chemistry, Chem 212, Exam 4 Material, Part 1. Stereochemistry. Stereoisomers have the same order of attachment of the atoms, but different arrangements of the atoms in space. These differences are responsible for slight differences in the chemical properties of these molecules. The effectiveness of a drug and possible side effects depend on which isomer is used. Stereoisomers occur in biological molecules such as carbohydrates, amino acids, and nucleic acids. Two classes of stereoisomers are conformers and configurational isomers. Conformers are not the same as stereoisomers. Conformers are basically we take rotation around a single bond and we look at the molecule from different viewpoints and different angles. Configurational isomers require bond breaking and bond making to have isomers become interconverted. An example would be 1-bromobutane versus 2-bromobutane. With stereochemistry, what we're looking for are molecules that have 4 different substituents attached to a carbon center, called a chiral carbon, and these display optical activity. The molecule I have up here on the top, we have a carbon in the middle here, and we see that it has 4 different things directly attached to it. This carbon right here in the center would be our carbon center, known as a chiral carbon. Here's another example of a chiral carbon. It has 4 different groups attached, and one way that we can indicate if we have a chiral center is we can use an asterisk next to that carbon to show that that is a chiral center. Enantiomers and the tetrahedral carbon. Enantiomers are a pair of molecules related as a non-superimposable mirror image. A pair of enantiomers differ only with respect to chirality, and in all other aspects are identical. The boiling point, melting point, and density are the same. I find that building models makes this a little more easier to understand. If you go ahead and take a carbon and put 4 bonds on it, and you can use 4 different colored balls at the end of it, put one on the table and then make its mirror image. And this way you can then look at the fact that they are mirror images, but they're non-superimposable, meaning if you took the carbon of one and place it on top of the carbon of the other, not all of the substituents line up the same. In this illustration, I go ahead and I've marked the different groups with 1, 2, 3, 4. Examples of enantiomers. Molecules that have 1 carbon with 4 different substituents have a non-superimposable mirror image. That's its enantiomer. Build models to see this. In this drawing, you can see that fluorine, carbon, and hydrogen are in the plane of the paper. Chloride is going back and bromide is coming out. And then we have its mirror image. We have carbon with fluorine going up again in the plane of the paper here, and carbon and hydrogen all in the same plane. And we have chloride coming back and bromine coming out. Make these 2 models, and then if you put one on top of the other, you'll see that they're non-superimposable. Another way that we could take a look at the term non-superimposable, if you go ahead and take your hands and put them together and have thumb to thumb and pinky to pinky, and you can see that your hands are mirror images. Now if you go ahead and take your left hand and go ahead and face it palm down to the ground, and then on top of that put your right hand palm down, notice that your fingers no longer line up. They're non-superimposable. Your thumbs are on different sides, and none of the fingers line up. They are mirror images. They're non-superimposable. The reason for handedness, this is known as chirality. A chiral molecule does not have a plane of symmetry. It is not superimposable with its mirror image. Taking a look at the structure on the right, we can see, we even have a model version of it, we can see that we have a CH3 on the top, and I think the model's a little bit easier so you can take a look at the plane of symmetry. If we look down the middle of this molecule here, it's basically all these are in the same plane as each other. Notice that the right side of the molecule is different than the left side, so it does not have a plane of symmetry. In order for the molecule to have chirality, in order for it to be optically active, it cannot be symmetrical. There are 2 non-superimposable ways that 4 different groups or atoms can be attached to 1 carbon. The molecule that's chiral can rotate plane polarized light. In the biological world, chirality is very important. One enantiomer may be a drug, where its enantiomer may be completely ineffective. Chirality center, the sp3 carbon to 4 different groups, usually indicated with an asterisk. Now the term center makes us think there's only one chiral center. We can have molecules with more than one chiral carbon. So don't let the word center make you think there's only one symmetrically in the middle. They just call it a chiral center. So looking at the models on the right hand side, let's add some asterisks to it. And again, we can indicate a chiral center or a chiral carbon using an asterisk. An achiral molecule has a plane of symmetry that divides it into 2 entire pieces that are exact mirror images. Propanoic acid is achiral. We can see that if we take a look down on this model, if we take a look down on the center here, that both the right and the left hand side are identical to each other. It has a mirror image. This example here, an Erlenmeyer flask, has a plane of symmetry. The right and left hand side are the same as each other, whereas your hand does not have a plane of symmetry. It's going to be chiral. The flask is achiral. Your hand, we can think of it as being chiral. Chirality centers in chiral molecules. A chiral molecule usually has at least one chirality center. We've actually been working with molecules that have chiral pieces to it, chiral features to it, but we haven't brought them out. Take a look at this. This is 5-bromodecane. When we have a carbon that has more than one hydrogen, it's impossible for it to be a chiral center because it has to have 4 different things on it. But when we get to this 5th carbon here, notice that I have a bromo, which is different than the hydrogen, and the left-hand side has a different number of carbons than the right-hand side. So this carbon right here does have a chiral center. Groups are considered different if there's any structural variation. This includes a different number of carbons, a different halogen. It also includes if you have a double bond on one side but not the other. In cyclic molecules, we compare it by following each direction in a ring. Let's take a look here. We have an example here of something that's achiral, and this one over here, which is chiral. We have a plane of symmetry in this molecule. When we look at the model itself, we can see the plane of symmetry. Now, it's more difficult to see the plane of symmetry when we draw the structure on paper, so keep in mind models will help us see the 3-dimensional aspect of it. Here we have 2-methylcyclohexanone. We do not have a plane of symmetry. Working our way down on this molecule, if you go to the left side and to the right side of where this carbon is, notice that we have something different, in this case a double bond oxygen, where the other side doesn't have that. This carbon here has 4 different groups. It doesn't matter that it happens to reattach on the other side. That's not what we're concerned with. We're concerned with it having 4 different groups. This is a chiral center. Optical activity. This is a sketch of a polarimeter. The light source comes in, and keeping in mind, light goes in all directions. But when we put it through a polarizer, only light of one direction is allowed to come through. When the light that is polarized comes through your sample, if the sample has optical activity, it'll rotate that plane polarized light into a certain direction from a certain angle from the original direction. It's this angle here that can be measured, and this is how we describe optical activity quantitatively. Light restricted to pass through a plane is plane polarized. Plane polarized light that passes through the solutions of achiral compounds remain the same. There's no rotation of the light. Solutions of chiral compounds rotate plane polarized light, and the molecules are said to be optically active. The angle between the entrance and exit planes is the optical rotation. When we're talking about polarization here, it's the same polarization when they talk about sunglasses, for example, that are polarized. I put a video on your class website about polarized sunglasses if you're interested in checking that out. Optical activity. Well, the light can be rotated either to the right or to the left. When the plane of polarized light is rotated to the right, in the clockwise direction, it's called dextrorotatory, or we can indicate it with a capital D or lowercase d, a plus sign, and in chemistry, if we take a look at the right-hand side over here, we also call them R. In this class, we're going to become familiar with all the different notations of explaining optical activity. When the plane polarized light is rotated to the left in the anti-clockwise direction, it's known as lever rotatory, or L. The L could be capital or lowercase, or we could have a minus sign. So in the chemistry version, we also have R and S. R is when it's going into the right-hand direction, going clockwise. S is when it's going in the left-hand direction, going counterclockwise. So S would match L, lever rotatory, where R would match D, dexter rotatory. It's going in the right-hand direction. We see optical activity in all the amino acids with the exception of glycine. What we see here is the general structure for an amino acid. We have the nitrogen on the left-hand side and the carboxylic acid on the right. It's this R group that changes with the different amino acids. Glycine, the smallest of the amino acids, happens to have a hydrogen as an R group, and you can see then that this carbon here is not optically active because it has two of the same things. Here's an example of alanine, L-alanine and D-alanine. They're optical isomers or enantiomers. Almost all biologically important molecules that display optical activity are L, lever rotatory. Why don't you go ahead and build the model of both L-alanine and D-alanine and take a look at its optical properties. It's not superimposable on each other. How we measure optical activity is through what's known as specific rotation. Specific rotation is a way to compare rotation in optically active molecules that are chiral. Specific rotation can be calculated using the observed rotation divided by the path length and the concentration. Specific rotation is that observed for 1 gram per milliliter in solution in a cell with a 10 centimeter path length using light from sodium metal vapor at 589 nanometers. The specific rotation of an enantiomer is equal in magnitude but in opposite sign. What this means is, let's say we have an L enantiomer and we are also testing its corresponding D enantiomer. Let's say that the L enantiomer rotates plane polarized light in the counterclockwise direction. Let's say it's just 10 degrees. Well, its enantiomer would rotate it also 10 degrees, but in the opposite direction. So the value of the specific rotation for each enantiomer is the same, but the sign would be different based on did it rotate to the left or to the right. Here is some specific rotations of some organic molecules. Penicillin minus 235, sucrose minus 66.47, camphor minus 44.26. Remember earlier we talked about most biological molecules are left lever rotatory? Cholesterol minus 31.5, morphine minus 132. We do have one that rotates it to the right, monosodium glutamate, MSG. Acetic acid and benzene, they don't have a chiral molecule, so they don't undergo any type of rotation. Louis Pasteur discovered enantiomers in 1849. If you recall, just a few slides ago, we said that enantiomers have the same melting point and boiling points and a lot of the similar physical properties. So they didn't even really discover that these existed until Louis Pasteur discovered that sodium ammonium salts of tartaric acid crystallized into right-handed and left-handed forms. This is pretty cool. He was able to make these giant crystals, and he noticed that they were non-superimposable mirror images. The optical rotations of equal concentrations of these forms have opposite optical rotations. So he discovered that you get the same value, but a different sign. The solutions contain mirror image isomers called enantiomers, and they crystallize in distinctly different shapes. Such an event is rare. To determine if a molecule is right-handed or left-handed, we have a general method that applies to the configuration at each chirality center. We don't look at the whole molecule. We take a look at the chiral center. That's our focus. The configuration is specified by the relative positions of all the groups with respect to each other at the chirality center. The groups are ranked in an established priority sequence and compared. The sequence rules. Assign each group priority according to the Cahn, Cahn-Ingold-Prelog scheme. That's what that CIP means in the title there. The lowest priority is going to have the lowest atomic number. The highest priority is going to have the highest atomic number. What you need to do is to take a look at the model and have the lowest priority pointing away, and then look at the three remaining groups. Let's take a look at my R version first, since this has R first. My chiral center would be here, and I have 4 different things on there. Going up within the same plane as the carbon itself, I would have the highest priority, so that would be something with the highest atomic number. And in the same plane, I would have here the second highest atomic number. Now going back behind me, holding the lowest priority away from me, you can see I have number 4. So that would be the lowest priority. And let's say you had a hydrogen on your molecule. That would be hydrogen, for example. And then I have number 3 here. In some slides to come, we're going to be practicing looking at priority. Let's take a look, though, how we're going to see R and S. Since our lowest priority is away from us, we only look at these 3 here. Notice that if I were to go in order, number 1 starts here, and to get to number 2, I have to go in a clockwise direction. To get number 3, I continue the clockwise direction, and again, we're not looking at number 4, that's behind us. Notice that the order of 1, 2, and 3 in priority are going in the right-hand direction, going in the clockwise direction. So this molecule would be R. Where R comes from is from the Latin word for right. On S, we have the lowest priority away from us. Again, if you would build a model, and I would even put stickers on them, 1, 2, and 3, and you can rotate those around to match R and S. But hold the lowest priority away from you, so the 3 others are staring at you. Let's take a look at this one. I have priority 1 here. To get to 2, I have to go in a counterclockwise direction. To get to 3, continuing that counterclockwise direction, and to finish the circle, counterclockwise. This would be counterclockwise, S, and S comes from the Latin word sinister, meaning left. R and S configuration at the chirality center. This is also showing us the same thing, that you need to be looking at the molecule with the lowest priority away from you. So this is now what the viewer here, this eyeball, is looking at. In this case, we have 1, 2, and 3. This would be an R configuration. And one way that they talk about remembering if it's right-handed or left-handed, they're using a car wheel, for example. In order for you to turn right, you would turn the whole wheel in this direction. I also like to look at it from the point of a clock. If you had the noon hour at the top here, and you're going in this direction, you would be going clockwise. And so we're also talking about the direction going in the right-hand direction. On the S configuration, making your model again and holding it away from you like this, you could see that going from 1 to 2 is counterclockwise. The sequence rules: atoms are ranked according to their atomic number. The higher the atomic number, the higher the priority. A tie is broken by looking at the next atom directly attached until the tie is broken. If you have a double bond, it counts as 2 times to carbon. If you have a triple bond, that would be 3. An example would be this carbon double bonded oxygen. That would be counted as 2 times to carbon. If this sounds familiar, we did do this before. We did this when we did the E and the Z, when we talked about stereoisomers using carbon-carbon double bonds. Our 5-bromodecane is back. Let's take a look at ranking each of these 4 pieces. So on the right side here, we went ahead and rewrote the substituents. We have a hydrogen, we have a Br, we have a butyl group, that's this one here, it has 4 carbons, and we have 5 carbons here. Let's rank the following. Well, looking at our periodic table, we know right away that hydrogen is going to be number 4. That's the lowest priority. Bromide has a higher atomic number than carbon, so that'll be number 1. And if you take a look at this, we have a tie here, we have a tie here, we have a tie here, but here's where the tie is broken. This carbon has 3 bonds to hydrogen, whereas this carbon, it does have 2 bonds to hydrogen, but it also has a bond to carbon. So this one's going to be our winner, and so this is going to be ranked, not number 1, Br already has number 1. This will be number 2, and this will be number 3. So what we could do is, taking a look at our bromo, let's go ahead and put number 1 here. And we can have number 2 here, and number 3 here, and number 4 here. That's their rankings. Now, because this molecule is represented flat, not three-dimensionally, it doesn't have the dash wedge, solid wedge to let us know what direction it is, we cannot determine if this drawing is R or S. I can determine the rankings of each of them, but because these are all in the same plane as each other, they didn't give me enough information. So one of the things we also have to include besides ranking is I have to know in the tetrahedral form where they are. So included with your slides, I have the same piece here where I'm seeing where the tie is broken. I have a hydrogen bonded here versus a carbon here. And again, this would be 2 and that would be 3. So for this slide, we're only going to practice assigning priority order. So within each row, I have 4 different things. So we have 3 different examples we're going to work with. Go ahead and pause the video, rank them, and come back and see how you did. Let's see how you did. Hydrogen is 4. Oxygen has the highest atomic number. Carbon is tied, but the tie is broken as soon as we see that this carbon is attached to not only 1 oxygen, but technically 3, because one of these is double bonded. Hydrogen is the smallest atomic number. It's the bottom rank. Bromine is the highest. Next, oxygen, and then carbon. There are no ties in this case. This one was a little more straightforward. All right, this next one, I have nitrogen in 2 spots. Let's see how to handle that. First of all, I know hydrogen's number 4. Let's get that out of the way. If you want to go ahead and draw out some of these structures, if this makes it easier for you, notice this nitrogen has a hydrogen directly attached and a carbon directly attached. This one only has 2 hydrogens. This one wins. Our ranking is this is 1, 3, 4, and 2. On this slide, I want you to assign R or S configuration to these 5 different molecules. The first step is to assign priority and then determine if it's R or S by having the lowest priority away from you. Now in this case, I didn't make all the molecules have the lowest priority away from you. I changed where they're going to be because the format that you might be presented this question, there's 4 different places they can put the lowest priority. They can have it towards you, away from you, or to the side. You might want to go ahead when you're first learning this, make the models of each of these. Now you don't have to make the entire model. What I would do is I would take a carbon, put 4 different colors coming out of it, and then take some stickers with the numbers 1, 2, 3, 4, and then go ahead and after you've assigned priority, go ahead and take that model and put the stickers on the correct sites that say 1, 2, 3, 4, hold the lowest priority away from you, and then see how it compares to what's on paper. You don't get to use model kits on the test. So what's going to happen is you need to be able to look at something that's written on paper and be able to imagine the lowest priority away from you and then determine if it's right or left-handed. Let's go ahead and get started. Pause the video, assign priority, and then assign R or S. Come back and see how you did. For this first one, we didn't have any ties. We have fluorine being 1, oxygen 2, CH3 is the 3rd one, and hydrogen is 4. So what's happening is my lowest priority is over here. So to keep this away from me, I'm going to be looking at it from this direction. I have number 1 here. That means 2 is going in this direction. To get the 3 is going in this direction. And so by looking at it from here, we can see this is going counterclockwise. This is an S. So this one had a tie initially with carbons here and here, but this one won the tie. In this case, the lowest priority is actually coming out at me. Take your model and put the lowest priority towards you, and then flip it and put the lowest priority away from you. Do you notice that when the lowest priority is facing you, that actually the direction is opposite of what you see? So we need to be looking at this as though we're looking at it from behind the screen from back here. That means number 1 is here, 2 is going in this direction, and 3 is going in this direction. Now remember, we're looking at it from back here. If the lowest priority is facing it, it's the opposite of what we see. Doesn't it appear to be going S? But in reality, because we're looking at it from the wrong side, it is actually an R. Make the model and convince yourself of this. Lowest priorities facing us. I wanted to give you another chance to practice that when the lowest priorities is at you instead of away from you. So the way we're going to handle this is, because the lowest priority is in the wrong direction, it's facing us instead of away, it's the opposite of what we see. So I see this going in this direction, but because my lowest priority is towards me instead of away, it's not an S, it's actually an R. Remember, you're looking at it from the back side here. Here we have our lowest priority going to the right, so that means we're looking at it from this direction. And so I have 1, 2, 3. This would be an S. All right, I have hydrogen again going in this direction. It's going 1, 2, then 3. That would be an R. The reason why we want to know if it's R or S is because we're now going to be using that as part of its name. These are stereoisomers, just as the same as cis and trans were stereoisomers, and also the E and Z were stereoisomers. So we must include in the name if it's R or S, just like we had to include cis or trans or E and Z. Draw the structure of S2-bromobutane, and then also draw the structure of R3-methyl-1-pentene. Let me go ahead and take you through how I do this. What I do is I draw the carbon backbone structure and I look for the chiral piece. So I have a 2-bromobutane. That means I have 4 carbons in a row and bromos coming off of number 2. That means if I take a look at this carbon here, that I have a different number of carbons on the left-hand side and right-hand side. So I went ahead and filled in this hydrogen. So now you can see this is my chiral center here. Now this is not the answer. This is the backbone structure of where everything is. So I don't have my hydrogens in here. You might want to go ahead and fill in the hydrogens if you want. Now that we know we have 4 different groups, let's go ahead and rank them. Hydrogen's going to be number 4, it's the lowest. Bromine's going to be number 1. And we have a carbon tie, but the tie is broken when we have 2 carbons. And we have all of them ranked. Now that we have established the numbering system, the priorities, what I like to do is when I'm asked to draw the S or the R form of something, is I like to go ahead and just have a pattern ready to go. I like to do this systematically. Now, you can see that there's actually 4 different ways you can do this because there's 4 different R groups. What I like to do is I like to go ahead and draw this line here going up and down, and this one here to the left. This is in the plane of the paper. And then I go ahead and draw the dashed wedge going back, meaning it's behind me, and this is coming at me. And what I do is, because it's me filling in the 4 different groups, I can make this group going back number 4 and this top one number 1. So filling these in, I can see bromine is number 1. That will go here. Number 4, that's a hydrogen. Number 3, that's this one right here. That's a single CH3 group. And I have an ethyl group here, keeping in mind CH3 is on the terminal piece of that, then a CH2. And now I have drawn my S2-bromobutane. Taking a look at my numbers, 1, 2, and 3. It's just these 3 numbers here I have to look at. These are going in a counterclockwise direction. There's my arrow, this direction, this direction. Remember, we don't look at 4, that's going behind us. Go ahead and use the same technique for R3-methyl-1-pentene. Pause the video, come back, and see how you did. All right, I know hydrogen's number 4. Methyl is number 3, it only has 1 carbon. On the left-hand side, I have a double bond carbon. On the right-hand side, I have a single bond. Double bond counts as 2 times to carbon. That would be a higher priority, so this would actually be number 1, and that would be number 2. On the pattern, I still use number 1 at the top here, and number 4 is going back, but the difference in an R is that my number 2 is coming out at me while 3 is here. Let's go ahead and fill in the groups. I know number 1 is a carbon double bonded carbon, so that would need to be a CH group double bonded to a CH2. Number 4 is a hydrogen. Number 2 is an ethyl group, CH2, CH3, and number 3 is just a methyl group. Now I have R3-methyl 1-pentene. Let's check. I have 1, then going in this direction I have 2, and then 3 comes back this way. Remember, the lowest priority is away from me. This is the only piece I have to look at to determine if it's R or S.